What is competitive learning? It is suitable for unsupervised network training and applicable for an ensemble of neurons, example a layer of P neurons, not for a single neuron. Output neurons of neural network compete to become active. So there is competition between output layer neurons to become active and adapt the neuron M which has the maximum response due to input X. This implies that the output neuron that has the maximum response due to input X is selected at that instance of iteration of neural network. Only single neuron is active at any one time. So this is a salient feature for pattern classification in competitive learning. Neurons learn to specialize on ensembles of similar patterns. Therefore, they become feature detectors. So proceeding in this way, the neurons learn to distinguish patterns from each other. Therefore, they become feature detectors. Basic elements of competitive learning. A set of neurons that are all same except synaptic weight distribution. All neurons respond differently to a given set of input pattern. A mechanism to compete to respond to a given input. The winner that wins the competition is called winner takes all. So these are the four basic elements of competitive learning that are a set of neurons that are all same except their synaptic weights, and all neurons respond differently to a given set of input, and a mechanism to compete to respond to a given input is there in the network. Competition exists in between the neurons, and the winner that wins the competition is called winner takes all. That is, it will be selected finally amongst all others. Now we see the competitive learning rule. We adapt the neuron M which has the maximum response due to input X as WMTX is equal to max of I is equal to 1 to be WITX. That is the WX part in the WIXI summation relation. The maximum one is selected in this case, and del of Wi is equal to alpha x minus Wi if I is equal to m and is 0 if I not equal to m. This is for finding the weight vector closest to the input x. So weights are typically initialized at random values and their strengths are normalized during training, where summation Wmj on j is equal to 1 for all m. So that is weights, combined weights of all the neurons will be 1. If neuron does not respond to a particular input, no learning takes place. So this is another rule in competitive learning, that if neurons don't respond to a particular input, no learning takes place at that point. What is required for the neural net to encode the training set is that the weight vectors become aligned with any clusters present in this set, and that each cluster is represented by at least one node. Then, when a vector is presented to the net, there will be a node or group of nodes which respond maximally to the input and which respond in this way only when this vector is shown at the input. So, what it says is that the neural net encodes the training set such that the weight vectors become aligned with all the clusters present in this training set, and when a new vector is presented to the neural network, then there will be a node or a group of nodes which respond maximally to the input and thus signify that that vector is belonging to that cluster in which that node or group of nodes is present, and this will be done only for that type of vector to be included in that group. Hope this is clear. So if the net can learn a weight vector configuration like this without being told explicitly of the existence of clusters at the input, then it is said to undergo a process of self-organized or unsupervised learning. This is to be contrasted with nets which were trained with the delta rule, for example, where a target vector or output had to be supplied. So we saw in the case of supervised learning neural networks where we have to supply the target vector or output that should be matched for error calculations, and this can be contrasted with current competitive learning rule in unsupervised learning, in which there is no need to tell explicitly the existence of clusters at the input, that is the output vector should not be told, and it should undergo it implies the it implies undergoing a process of self-organized or unsupervised learning. So in order to achieve this goal, the weight vectors must be rotated around the sphere so that they line up with the training set. So the weight vectors must be aligned with the training set so that they can form clusters. The first thing is to notice that this may be achieved in a gradual and efficient way by moving the weight vector which is closest in an angular sense to the current input vector towards that vector slightly. So if we move weight vectors to the current set of input vectors from the training set towards that vector slightly, then we can move the weight vectors around the sphere. The node K with the closest vector is that which gives the greatest input excitation V is equal to Wx, since this is just the dot product of the weight and input vectors. As shown below, the weight vector of node K may be aligned more closely with the input if a change is made according to del Wmj is equal to alpha xj minus Wmj. So what it says is, this is the formula here. The weight vector of node K may be aligned more closely with the input if a change is made according to. This is the formula so that we can align the weight vector to the more closely to the input. Winner takes all learning. The winner neighborhood is sometimes extended to beyond the single neuron winner to include the neighboring neurons. So I like to emphasize at this point that the alpha here is the learning rate here, and the neuron with the maximum excitation is selected as per the competitive learning rule. Maximum response is judged by WIXI, and the neuron that is the winner uh, is the only neuron where weight updation is performed del W, and that is given as learning rate into input minus the weight of that neuron at that point of time, and for all other neurons there is no learning, so del W is 0. So the winner neighborhood is sometimes extended to beyond the single neuron winner to include the neighboring neurons. So sometimes we extend this rule to include the neighboring neurons so that we get the clusters. We move on to self-organizing maps. Self-organizing maps are aptly named self-organizing because no supervision is required. It is case of unsupervised learning. Self-organizing maps learn on their own through unsupervised competitive learning and attempt to map their weights to conform to the given input data. So self-organizing maps are unsupervised competitive learning networks that learn on their own and attempt to map their weights to conform to the given input data to form clusters. Thus, self-organizing maps are neural networks that employ unsupervised learning methods, mapping their weights to conform to the given input data with the goal of representing multidimensional data in an easier and understandable form for the human eye. Pragmatic value of representing complex data. So training a SOM requires no target vector. A SOM learns to classify the training set without any external supervision. So since it is unsupervised learning, we don't need a target vector. So this is the architecture of self-oriented maps. There is a set of input vectors initially at the bottom here. Then it is made up of input nodes and computational nodes basically. Each computational node is connected to each input node to form a lattice. So each of the computational node is connected to each of the inputs, and thus forming a lattice, and there are no interconnections among the computational nodes. So among the computational nodes there are no interconnections. The number of input nodes is determined by the dimensions of the input vector. So this is simple. The number of input nodes is determined by the dimensions of the input vector. That dimension refers to the number of variables or number of dimensions of the input vector. That will be the number of input nodes. Suppose we have an input as in 3 dimensions, so that will be 3 will be the number of input nodes. Now regarding weight vectors in the SOMs, weight vectors are of the same dimension as the input vectors. So given input vectors v1 to vn, each node will contain a corresponding weight vector of n dimensions w1 to wn. Terms used in self-oriented maps, vector quantization. This is the data compression technique. Self-oriented maps provide a way of representing multi-dimensional data in a much lower dimensional space, mostly 1 or 2 dimension. So this is also known as dimensionality reduction or vector quantization. Next term used is neighborhood. Next is output space that contains all the outputs range. And next is input space, that is the range of the inputs. So in this slide we see the working algorithm of self-oriented maps. So Kohanen is a type of self-oriented maps. So whose structure is shown in previous slides. So basically the structure self-rising map algorithm can be broken up into 6 steps. First one is to initialize each node's weights in the neural network. Then second step is a vector is chosen at random from the set of training data and presented to the network. So we choose a random vector from the training data and present it to the network. The next step is every node in the network is examined to calculate which one's weights are most likely the input vector. The winning node is commonly known as the best matching unit. So basically what it wants to say is that every node's weights are examined to calculate which node's weight is most like the input vector. Then that node which has the weight most like the input vector is chosen as the winning node, and the winning node is commonly known as best matching unit or BMU. The next step is to calculate the radius of the BMU. I mean radius will be that node's surrounding area. So as discussed in previous slides, one of the previous slide, that is sometimes we extend the best matching unit to more than one nodes. This value starts large. I mean the radius of the neighborhood of the BMU is starts large, and typically it is said to be the radius of the network initially, diminishing each time step. So we see the iteration to diminish the radius. Any next step is to any nodes found within the radius of the BMU calculated in step 4 here. This is step 4. So any nodes if found within the radius in step 4 are adjusted to make them more like the input vector. So these equations are basically that del weight updation competitive learning rule equations. So according to those equations we update the weights to make them more like the input vector. So any nodes which are found within the radius of the BMU are updated to make some weight changes in them to make them more like the input vector. The closer a node is to the BMU, the more its weights are altered. So the closer a node is to the best matching units, the more its weights are altered. Hope this is clear. So we repeat from step 2 to step 5 for n iterations. So what is the repetition? Next, again a vector is chosen from the set of training data, and again every node is a network in the network is examined again, and this is repeated again and again. So this is how the SOM algorithm works. The function for calculating the score inclusion for an output node is square root of summation on I ni minus wij whole square. So the node that has the lowest score becomes the winning node. Value of that node is closest to the input vector. So that is like a distance vector here. As a result, the weight vectors associated with the winning nodes are adjusted so as to reward the node for winning the instance. So the winner node's weight are adjusted so as to reward the node for winning that particular instance of iteration. Both of these are decreased linearly over the span of several iterations and terminates after instance. Classifications do not vary from one iteration to the next. So when there are no separate classifications happening from one iteration to the next, the algorithm is stopped. Finally, the clusters formed by the training or test data are analyzed in order to determine what has been discovered. So when the clusters are formed, we observe them to analyze what has been discovered. Neighborhood adjustments. After adjusting the weights of the winning node, the neighborhood nodes also have their weights adjusted using the same formula. So the BMU best matching unit has its neighborhood nodes adjusted using the same formula. The weights are adjusted for those nodes in the surrounding. A neighborhood is typified by a square grid with the center of the grid containing the winning node. The size of the neighborhood as well as the learning rate R is specified when training begins. Current applications of self-oriented maps include WebSOM, that is an organization of massive document collection that uses self-oriented maps to detect patterns in documents and arrange them in some categories. Next is classifying world poverty example. Given property stats for various countries, the SOM can organize the clusters geographically based on poverty levels. So basically, SOMs are used for classification and clustering.